Hello, in part 1 we discussed Kirchhoff's junction rule, and after the intro we will continue with Kirchhoff's loop rule. Kirchhoff's loop rule describes voltage conditions in an electrical network. The rule is: the directed sum of all voltages in a closed loop is zero. There are two views to the rule. First, we draw all voltage arrows in a loop in the same direction, either counterclockwise like here, but also it is possible to draw all arrows clockwise in a loop. Then we get the sum of all voltages is zero, or U1 plus U2 plus U3 is zero, and with concrete numbers minus 4 volt plus minus 6 volt plus 10 volt is zero. In the other view there is no dedicated direction of the voltage arrows. You can draw it as you prefer it, and you add all the voltages of the clockwise arrows and you add all the voltages of the counterclockwise arrows and set them equal. Here in our example we have the counterclockwise voltage U3 and the two clockwise voltages U1 plus U2, and we set them equal. U3 equal U1 plus U2. With concrete numbers, 10 volt is 4 volt plus 6 volt, and we bring this 2 to the other side. Minus 4 volt minus 6 volt plus 10 volt is 0. And you see that this formula is identical to this formula. For practical usage, you should always draw the voltage arrows in such a direction that they represent positive voltages, which means they start at the higher voltage and point to the lower voltage. At voltage sources it's easy because usually it's known where the positive and negative side of the voltage source is. At load it's sometimes tricky to find the right direction. Do your best assumption, and if you are wrong it's not a big problem, because then the result is a negative voltage, and then you know that the voltage drop is in the other direction than the arrow. One last remark: you can get this base form of the formula even with this view if you add all voltages with arrows in one direction and subtract all voltages with arrow in the other direction and set them zero. The physical background is that nodes are pointed with the same electrical potential or the same voltage. So we had at this node the same voltage or electrical potential. We had at this node the same voltage or electrical potential, and we had at this node the same electrical voltage or potential. Now it's easy to understand if we walk to a complete loop that all the increasing voltages must be equal to all decreasing voltages to get at the same potential of the starting point. The definition of a loop is a movement until we return to the starting node. A node is an electrical connection with 0 ohm electrical resistance. It has the same electrical potential or the same electrical voltage. Here another one, and here a third node. In this simple circuit we have 3 basic loops. The first one, we start here, plus U1 minus U3 minus U2 is 0, and we are back at the starting node. The second one, we start here, plus U3 minus U4 is 0, and we are back to the starting node. And finally we start here, plus U1 minus U4 minus U2 is 0, and we are back in the starting node. But there are also more complex ways allowed. We see it in our example L4. We start here, plus U1 minus U3 plus U4 minus U3 minus U2 is 0, and we are back on the starting node. So you see, you can do very complex movements. It's only important that your starting and end point is equal, and all voltages where the arrow is showing in the same direction as your movement are added, and voltages where the arrow is showing against the movement direction is subtracted. Finally, we want to do two exercises to get more familiar with formulas. I have signed the nodes with the dots, and the voltage in this example is U1 is 12 volt, U2 is 3 volt, and how big is U3? Please press the pause button and do the math yourself. Here's the solution. Here we have our loop. Now we set the counterclockwise voltage U1 equal to the sum of the clockwise voltages U2 and U3. Now we bring U2 with a minus sign on the other side and swap the formula. And with the concrete voltages we get U3 is 12 volt minus 3 volt, and finally U3 is 9 volt. In our exercise 2, the circuit is a little bit bigger. U2 is 6 volt, U4 is 7 volt. How big is U3 and U1? Please press the pause button and do the math yourself. Here's the solution for exercise 2. We have here our loop. We set the counterclockwise voltage U3 equal to the clockwise voltage U4. Put in the concrete number and get U3 is 7 volt. We have here our loop, and set now the counterclockwise voltage U1 equal to the sum of the clockwise voltages U2 and U3. U1 is U2 and U3. With concrete numbers, U1 is 6 volt plus 7 volt, U1 is 13 volt. That's all for today. If you like my video, give me a thumbs up and subscribe my channel. And to be informed about new videos, activate the bell. Bye bye.